quantum algorithms. A really simple algorithm that I would like to start off with is the Deutsch algorithm. So we plan to cover two algorithms today. One is Deutsch algorithm and the other is Grover's search. The Deutsch algorithm was one of the earliest algorithms proposed to be used on quantum computers. And this really shows, though in a very modest sense, how quantum information processing can accelerate certain tasks. And the meaning of acceleration will also be clearer as to what is the promise that these quantum information processes hail for the community. So let's frame this algorithm first. David Deutsch, as you might know, is one of the famous Oxford guys who invented this algorithm, and he came up with the idea of what is called the many worlds interpretation. He was one of the strongest proponents of the many worlds interpretation of quantum mechanics. So the Deutsch algorithm goes as follows. Suppose I have a string of bits, zeros and ones, 0 and 1, and I have n of them. And I define a function f that acts on this string and yields a binary number, 0 or 1. So to exemplify this, suppose my n equals 1. So I'm looking at four kinds of functions. I'm looking at one function with two possible inputs. So I could have f equals 0, f of 0. This is some binary bit, 0 or 1. I can have f of 1. The function acts on 0 and 1. So I'm just considering 1-bit strings. The 1-bit strings are zeros and ones. Just a 0 and just a 1. So this function can act on this string. So it's acting on this bit. F acts on 0 and yields something. The output could be 0 or 1. So this output could be 0 or 1, either of them. And when f acts on the other kind of string, which is 1, the output could be 0 or 1. Now I distinguish between two kinds of functions. One I call a balanced function, and the other I call a biased function. Now, example of a balanced function is that f acts on 0 and yields me some number, say 0, and it acts on the other bit 1 and yields a number, a binary digit 1, which is different from 0. So when f acts on 0 and on 1, the outputs are different. Alright? So this is one example of a balanced function. The other possibility is that f acts on 0 and yields 1, and f acts on 1 and yields 0. So we have two kinds of balanced functions. Right? The other kind of a function is a biased function. And in a biased function, as you can imagine, that f acts on 0 and the output is the same when f acts on 1, and this output could be 0 or it could be 1. It's just like having a coin, and you want to decide whether the coin is balanced or is it biased. Balanced means that there is a head on one side and a tail on the other side. And biased means that both of those sides have either heads or tails. So you want to distinguish between the two scenarios, whether the coin is balanced or is it biased. So that's what the two kinds of functions are. And you would like to, distinguish between these two kinds of functions. So that's the task at hand. So we have a function f and we would like to tell whether it is biased or is it balanced. And in order to, the easiest approach to do this is, if you look at this classically, you could just have a box, a black box that implements the function f. You input a state 0. Now this is a classical state coming in 0, and you note what the output is. You have a detector, a classical detector that notes what the output is, whether it is 0 or 1. And then you repeat the experiment. So you do the experiment once in this fashion, and then you repeat the experiment in another fashion, and you see what the output is. So by doing these two queries, you can determine whether the function is balanced or biased. So you need two queries classically. However, let's take advantage of the idea of superposition and initialize a quantum computer so that both of these inputs are fed into the quantum computer at the same time, and our idea and motivation is to do one-shot determination and discrimination between a balanced and a biased function. So we want to do it in one shot. And right now our n is 1. You can have longer bit strings as well. And you want to distinguish between the different kinds of functions by just doing the experiment once. So instead of having two queries, let's see if we can reduce this number to a single query. Right? So if I were to design a quantum computer or a quantum circuit, let's call this circuit U sub f. So this is a unitary propagator or a unitary operator, and let's suppose that I have two inputs. I encode my initial states as a quantum state, so I encode as ket 0, and then I have an auxiliary qubit. It is also in the state ket 0, and somehow this unitary function is designed in a manner that nothing happens to the first qubit, but the value of the function acting on this state is encoded into the second qubit. So I'm hypothesizing that we can make a quantum circuit that does this. It takes two inputs. One is on this channel we are inputting our quantum state. We would like to find out what is the role of a function on this quantum state. And we also put in an ancillary qubit or an auxiliary qubit, and just design this quantum circuit so that the action of f on this logical label is reflected in the state of the second qubit. So this is one possible way of doing this task. So, but you would have to run this circuit once with ket 0 as the input, and then you would have to run this circuit once with ket 1 as the input. So in each case you will determine what this function, the value of the function is, but you will have to do two queries. One with ket 0 as the input and one with ket 1 as the input. Got it? Now can you come up with a circuit? We've seen many circuits in the past. Can you come up with a circuit that does this? What kind of quantum circuit or logic gate needs to be applied here? Yes.
How did you decide that the auxiliary qubit has to be can be just?
So we have to initialize it in some manner. This is one possibility, that this is ket 0. Could be anything else. Yes?
It's a control knot.
Control knot. But control knot is always going to invert this. So it's similar to a control knot. Suppose I do the following. So what I do is on this channel, so So let me redraw this. A UF that does the following will work. I have an input ket A could be 0 or 1. This is ket 0. Something happening here, I'm building a quantum circuit that does something, and this output remains ket A, whereas this output is this state 0 plus the exclusive OR of the function acting on this logical bit. So I need to implement a circuit that does an exclusive OR. So what is the truth table for an exclusive OR? Exclusive OR is represented by this function here. An exclusive OR, I think, is represented in this fashion. So what it does is, if the inputs are the same, the output is 0. Inputs are different, the output is 1. So you do an exclusive OR of the state of this qubit 0 with the function acting on A. So you build your quantum circuit in such a way that this scheme is implemented. And why do you need two outputs? Because you have two inputs. The number of outputs needs to be the same as the number of inputs if you were to do a unitary operation. Otherwise the operation will be non-unitary, because a unitary operation is reversible. If you so an AND gate, for example, this gate that is drawn here is non-unitary because it takes certain inputs, gives you an output, but looking at this output, you cannot tell what the inputs are because there are two possibilities here. If the output is 1, the 0 could be on the first bit or it could be on the second bit. So you cannot reverse this gate. So if you want to do unitary operations, which most quantum computing is, you would have to have the same number of outputs as the number of inputs. Otherwise your gates will not be reversible. So one possibility of determining this function is, and by the way, if you take the exclusive OR of 0 with f of A, this is always going to turn out to be f of A. Correct? So you have encoded the output of the function acting on this state in the second qubit, in the state of the second qubit. Alright? So you need to implement this exclusive OR gate on a quantum computer. Alright? G. Sorry? So you have to design this in a manner, so you have to build this UF so that it does this function, it implements this function. It's not a straightforward exclusive OR operation. You have to design this quantum circuit so that it achieves the desired task. For example, looking at these possibilities, this could be a homework problem. Say our function does this. Can you design a UF that implements this and draw the circuit model for UF in here, in this box here? Okay, so that's what engineering the quantum computer means. You have to design out of many elementary gates something that goes inside the black box. Such a black box, by the way, is called an oracle. Now, what an oracle does is, I'll explain what the oracle does. It's a quantum oracle. So let me get a bit further in this description. Suppose I do the following. I have two inputs, two qubits. One is my working register. My bit is encoded on the first channel. And I put this in a quantum state, ket 0 or ket 1. And I initialize this as ket 0. And then an ancillary qubit I also initialize as get 0. Alright. So let's see how all of this works, and then I think the ideas will be much clearer. So this is my working qubit, and this is my auxiliary or ancillary qubit. I want to add this ancillary qubit because I want to encode the output perhaps here. I need to have this ancillary qubit here. So what I do now is I put a Hadamard gate here on the first qubit, and on the second qubit I put a NOT gate followed by a Hadamard gate. Alright. So I'm going to implement the Deutsch algorithm. I'm going to find out whether my function is balanced or whether it is biased First of all, I need to initialize my quantum computer. So I input with get 0 on my working qubit and get 0 on the ancillary qubit. So let's suppose that the state here is denoted by psi1. What is this psi1 going to look like? What is the ket representation of psi1? So what's the state of the first qubit after the Hadamard? Right, so it's 1 over under root 2 ket 0 plus ket 1. And the second qubit? Right, 1 over under root 2 ket 0 minus ket 1, right? So I can also write this as 1 half 0 0 minus 0 1 plus 1 0 minus 1 1. So I created a superposition in a sense. Now I would like to put in my oracle here. What this oracle does is that it keeps the first qubit as it is. So let me describe what the oracle does. So my first qubit is in a state x. X could be 0 or 1. The second qubit is in some state q. Q could be 0 or 1. And there's a unitary operation UF that acts on this input state. So I'm defining what does this black box do. Alright. So this is my definition. So I'm putting 3 signs here. I have built my black box, which is called a quantum oracle, and I'm going to describe why is it called a quantum oracle, so that the action of this black box on any input state that comes in is as follows. Nothing happens to the first qubit, and the second qubit acquires this form. Alright. Now I have built my unitary operator. This is my unit. I want to achieve this unitary operation. This is a mapping in Hilbert space. I take an input and I get this. I can feed in different inputs 0, 0, 0, 1, 1, 0 and find out what the outputs are going to be for a given f. And for that given f, the task of a quantum computing engineer is to design a network of logic gates so that this task is achieved. Right? Now, why is this called a quantum oracle? A quantum oracle is a tool that helps you distinguish one solution from many possibilities. So it can tell you what the function is. And it can light up when you get a desired result. Suppose you're searching something and you're searching for a particular string. If the oracle can tell you that it gives you a certain output, and if the search string is input, it is available to the input, it gives you a signal that, oh yes, we found our search. So it's a tool or a machinery that helps you discern your solution from other possibilities. So if the solution is found, it goes bingo, yeah, I found the solution. Just imagine if you were to factorize the number 15. So you have number 15. One possibility is to design an algorithm that finds out the prime factors of 15. But suppose you are given, it hits upon 5 and 3 in its input space. The oracle can tell, yes, 5 and 3 have been found. They work as a prime factor pair of 15. So the oracle tells you that 5 and 3 is the solution. If you find 4 and 4, it's not a solution. So if the oracle is fed with 4 and 4, it can tell you, no, this is not the solution. But if it is fed in with 5 and 3, it can declare that, yes, I found the solution. That's what a quantum oracle does. But it has to be pre-designed. So the oracle is pre-designed so that it can look for the prime, it can test whether the inputs are prime factors of the number 15. That's what an oracle does. So now we have this unitary operation. This unitary operation has to be built into this UF. Now you can do this as a homework, that if I have any one of the 4 possible function sequences, what kind of quantum logic gates do I need to build this oracle? Yes?
So what does f of x mean?
F of x means f of 0 or f of 1.
So do we know the form that f of x has?
So we do not know the form, but we would like to distinguish and tell whether f is balanced or biased. So there is some f and it's either balanced or biased. So this algorithm discerns which kind of function it is.
What is the balance function bias behind it?
So balance function is that gives me 2 different outputs for 2 different inputs. 0 and 1, 2 distinct outputs for 2 distinct inputs. 1 and 0, 0 and 1 for 2 distinct inputs. However, a biased or an unbalanced function always gives the same output, no matter what the input is. Alright, so this unitary operator is to be built into this oracle. So what's going to happen to the output here? So this is my psi 1. What is my psi 2 going to be? Which is the oracle acting on psi 1. So you can use this argument here. So let's try to do this. Do you understand what is meant by an oracle? Let's complete the argument and let's revisit the idea of an oracle. So what this does is 1/2, put a big bracket. So nothing happens to the first qubit, and I take the exclusive OR of the second qubit with the action of f on the first qubit. So 0 plus exclusive OR of 0, right? This is what the unitary operator does. This is what the oracle does. So I'm just translating this into here with specific inputs. So if x is 0 and q is 0, I get x here and q exclusive OR with f acting on this way.
Sir, here x is representing of first qubit or second?
First qubit.
So, all the way.
Hmm?
Not in the first qubit, all the way.
So I'm just mapping this. So unitary function act. This is my first qubit. This is my second qubit. The first qubit remains unchanged, and the second qubit, you take the exclusive OR of the state of the second qubit with the function acting on this label here. Minus 0, 1 exclusive OR with f acting on 0, plus 1, 0 plus exclusive OR f acting on 1, minus 1, So I just simplify this. Exclusive OR of 0 with anything is just the second thing, right? Minus. So this is the state that is achieved over here. Right? So I still don't know what is F0 and F1, the four possibilities for F0 and F1. So what should the next step be? No, I don't want to assume anything at the moment. So what I would now like to do is get 0, f of 0 minus 1, f of 0. Plus get 1 All right, so now things are getting a bit clearer. Can you tell what's going to happen if the function is balanced? If the function is balanced, this output, f of 0, if this is 0, suppose this was 0. The function is balanced, if this was 0, this would be 1. Right? And 1 exclusive OR with 1 is 0. So here if I have, so if this were, I have f of 0 here. So if this were balanced, then this would be 1. So possibilities is f of 0 is 0, f of 1 is 1. Right, so this will be 0, this would be 1. Then this would be 1 and this would be 0. The other possibility is that this is 1. If this is 1, this is 1, this would be 0. Right, so can you determine a form which is consistent by determining whether the function is balanced or biased? So if I put 1/2 here, this is get 0. If f is, so what is this thing equal to? Can I come up with a general form for this? Can I write this qubit, this 2-qubit state in this form? Right? Plus get 1. This will be minus 1 place for f acting on 1. So what's happening here? This function could be 0. If suppose f of 0 is 0, this thing here. And this is ket 0 minus ket 1. Ket 0 minus ket 1 with a plus sign. That is minus 1 raised to power f of 0. F of 0 is 0. Minus 1 raised to power 0 is 1. However, if f of 0 is 1, then you get a 1 here, and 1 exclusive OR with 1 is addition modulo 2 gives you a 0 here. So it's the same thing with a negative sign. That's why I put minus 1 raised to power f of 0 here. If f of 0 is 1, this would be minus 1 raised to power 1, which gives a negative sign. So everything is working here. Yes. So right now there is no balanced or biased. It's just, so what I'm doing here, this is my input state. This is a state that we have achieved at this point in time. Now we apply this function, this oracle. This oracle is applied to this input state and I get an output state. Now I would like to determine what the output state is after the oracle. So I'm just taking this recipe and plugging it in here. So there is no concept of balanced and constant as yet. Now what I would like to do, so do you understand this final step? No? So do you understand this step? So I've just factorized out the first qubit ket 0 here and written these two qubits, the second qubit together. Now the possibilities, this function of 0 could be 0 or it could be 1. If it were 0, then this would be ket 0. What would this be? 1 exclusive OR with 0, which is 1. So 0 minus 1, ket 0 minus ket 1, ket 0 minus ket 1. Right? If this were 1, then this would be ket 1 minus ket 0, which is just the inverse of this. Now how do I take into account this inversion? I just put in a minus sign where needed. Now that minus sign where needed is incorporated by this minus 1 raised to power f of 0. If this factor is 0, then minus 1 raised to power 0 just gives me 1, so I'm left with this being positive. However, if this takes the form form 1, then this is minus 1 raised to power 1, so it imparts a negative sign to this, so all of this is inverted. So this is the proper way of writing this state cycle. Now, what is your guess? How would I like to do a measurement? How would I like to tell whether my output is balanced or is it constant, biased? Any guesses? So what I could do, what if I put a Hadamard gate here? Let's see what's going to happen. So if I were to put a Hadamard gate on the first qubit, so I can also write the state psi 2 in the following form. 1 over under root 2 minus 1 ket 0 plus minus 1 ket 1 So now I would like to do a Hadamard gate. So on this psi 2 I apply Hadamard operation just on the first qubit. And if I want I can apply a Hadamard gate on the second qubit as well. But it doesn't really matter. What this Hadamard gate here would do is that it will bring this state back to ket 1. Right, but that's not really needed. But let's for the sake of completion, do this, because now we have a separable state, by the way. We can write down the state of the first qubit and the state of the second qubit. There's no entangling as yet, and there will be no entanglement in this algorithm. So what's going to happen when the Hadamard gate acts on the first qubit? You already know what the recipe for this is. 1 over root 2 minus 1 is for f of 0. This will become 0 plus 1 under root 2. Big parentheses minus 1 f 0 minus 1 over under root 2. Big parentheses. And this is just gone back to get 1. Because when the Hadamard gate acts on the second qubit, it just converts it back to get 1. Now let's just look at the first qubit. I'm not concerned with the second qubit, right? You already know what this is. So the first qubit will go as follows: 1 over under root 2, 1 over under root 2, minus 1, f of 0, plus minus 1, f of 1, get of 0, plus minus 1, f of 0, minus minus 1, f of 1, get of 1. Now is it possible to distinguish between balanced and constant or biased functions? Isn't it true? So if f0 and f1 are different, which means that if the function is balanced, which means 1 is 0, 1 is 1, then this term disappears. But this term survives fully. So this becomes a 1, this becomes a 1, this becomes 2. That 2 cancels off with this, you're left with get 1. If the function is biased, which means both of the functions give you the same output, then these terms will survive. This term is going to cancel out and you're going to be left off with get 0 only. So now I put a detector over here, of course preceded by a beam splitter that can produce 2 output channels, and I put 2 detectors here, and by seeing which detector clicks, I can tell in one go whether the function is constant or is it balanced. So if f is balanced, then this term just withers away, because this will be minus 1 raised to power something minus minus 1 raised to power the same thing. So this will be the difference of 2 like numbers, that will be 0. So the output, let's call this output say psi 3. Psi 3 will be simply get 0. This term is going to survive. On the other hand, if f is I'm sorry. This is what's going to happen if f is balanced. Correct, isn't it? Balanced means the f's are different. If f's are different, suppose this is 0, this is 1. Right, just alright, just a minute. If f is balanced, which means that these two things are opposite, so this will be negative. So we'll be left with get 1. And if f is biased, biased means it's constant for both of them, then we will be left with get 0. Correct? So in one go, we have determined whether the function is constant or it is balanced. So we do a measurement over here on this qubit. Now let me recap a few things here. This is the Deutsch algorithm, a simple example of a quantum algorithm, one of the earliest ones. It solves a certain problem. The problem is you have a function f that acts on a binary string, and there are two kinds of functions, constant or balanced, biased or balanced. Constant means the same output for everything, which means biased. So constant or balanced, and you have to determine whether the function is balanced or it is biased. Now the function is already there, right, because it has been encoded into this oracle. What the oracle does is you already built a function and you would like to tell whether that function is constant or balanced. So you would like to investigate a property of that function. You could do this in one go by initializing your quantum computer in a superposition state. So what we're doing here is that we're creating a superposition here. And that's a general scheme of many quantum algorithms. You take some inputs in the Zeeman basis or computational basis and create a superposition. And you just feed in that superposition into an oracle. Now the oracle has implemented the function already. So this seems kind of paradoxical, that when you were building this quantum computer, you knew what the function is and you had built it already. But this is just like this question of you determining whether the function is constant or it is balanced by looking at what the outputs are in one go. Now you have a certain output and then you project back the superposition into a measurable state. So you're measuring back in ket 0 or ket 1. And the answer to your question has been ingrained into what output you are measuring here. So here we started off by creating a relative phase between components of the superposition state. And that relative phase has an impact on final probability outcomes. So even though we cannot directly measure the relative phase, that relative phase has somehow got to bleed through to the probability amplitude of the final state, so that the probabilities, which are modulus squares of these probability amplitudes, tell you what the function is. So even though measurement is now collapsing the state into ket 0 and ket 1, by looking at the kind of collapse, what is this state collapsing into, you can tell what function it is. Alright, any questions about this? Yes?
Are those inputs arbitrary? I mean, can they be in a superposition?
So if they were in a superposition, you wouldn't need these Hadamard gates. So these Hadamard gates are just meant to create a superposition, so that superposition is fed into the quantum computer. Otherwise you will have a scenario just like this. So, but then you will not get any complexity advantage. The query complexity of this algorithm is 1, which means in one go you can tell whether the function is constant or balanced. The classical query complexity is 2. You need 2 function evaluations with different inputs. You input first 0 and find out what the output is, then you input 1 and find out what the output is, and from the 2 outputs you can tell whether the coin is balanced or it is biased. Suppose you have a coin and I ask you whether it is balanced or fair. You would observe it from one side and then you will flip it over and do another experiment. So you need to do 2 queries to the coin to determine whether it is biased or balanced or fair. But now the query complexity that is achieved quantum mechanically is just 1. So in one shot you can tell whether the function is constant or balanced. Yes?
So any decision on the if balanced or biased means whether to bar one of the vectors is independent.
Yes. They're inseparable, right? So what's happening here, there are different ways to look at this. Initially, look at those 2 qubits. This is a correlated state. This is not perfectly entangled. and it's not perfectly separable. The degree of entanglement is not maximal here, psi 1. So what you're doing is, imagine that there are 4 paths. Each path comes with a sign. Now there are certain paths that are destructively interfering, certain histories that are just withering away, they're opposing one another, and you're just left with 2 possible paths, 0 and 1. So there's some destructive interference taking place, and you have designed your algorithm in such a fashion, and your quantum circuits are built in such a fashion that even though you're getting collapsed measurements, still your measurement is telling you something about the function. So, and how do you achieve that? This is the general scheme. You initialize your quantum computer by some input states, you create a superposition, let it go through an oracle, and then you bring it back. Just like 2 waves, you create the waves, create a superposition, let them interfere, and then bring them back and make a measurement. Remember the Mach-Zehnder interferometer? You create an input state, you create 2 paths for the photons, and then bring them back to the final beam splitter. Exactly the same idea is at work here. Get a question? Yes. A query means how many times does this algorithm run? Measurement is something else.
Can we make a system classically that it has 2 results and runs once?
And just runs once? Yes, but those 2, so having a system that has 2 inputs, you're doubling the number of resources. So the resources can be traded off by the number of inputs or by the number of times the experiment runs. So, right? So it's the same thing. Number of resources that are input into the system versus the number of times the experiment runs is just the same. Both of them add to the query complexity. Yes.
सर जो हमने क्वांटम सर्किट ये डिजाइन किया है एट अ मार्ट और नॉट गेट ये सारा हमारा डॉइच एल्गोरिथम है ना
Right, so this is the Deutsch algorithm, yes.
So basically the purpose is to find out whether the oracle function is biased or balanced.
And by the way, the function has already been inbuilt into this. Right? So let me give you another example, a more sophisticated example, and that is of Grover's search. Now suppose you have n qubits. Right? N qubits. So with n qubits, you can create a superposition of 10 to the power 8 states, right? So let's call capital N as 2 to the power n. So this is the number of states, and we have n qubits. Suppose you also have an n-bit binary string. Right, so example 0, 0, 0, 1. There are n of these bits. So with these n bits, you will have 10 to the power n possible strings. And you would like to find out one particular string. You want to search for one particular string. It's just like a font directory. You have a directory of numbers, a large directory of numbers, and you want to find out for one particular number, my phone number, from a font directory. So doing a search, and you have n bits, and which means that each number is n bits long, and since each number can have 2 values, zeros and ones, it's a binary directory, there will be 10 to the power n, small n, or capital N possible numbers, and you want to find out one of them. Okay, so now what we would like to do is we would like to design an oracle for this, an algorithm for this, and we want to search out a desired string from a large database of strings. Suppose my input database, my n-bit strings are represented by this number x. Now I'm writing this x in bold, right? Bold. So this is a sequence of n bits, some sequence of n bits. And the number that you would like to search for is, let's denote this by x. star. Now I would like to build an oracle, right? What the oracle does is implement a function. The function goes as follows. So what I would like to do is, when f acts on x, which is not equal to my desired number, I will get 0. My output is a single bit 0. And if my f finds as an argument x star the string that I'm searching for, my output is 1. So this is the logical function that I would like to build quantum mechanically into the oracle. Alright. Yes?
X is near all possible numbers.
X
So X has all possible numbers that are
given all possible numbers. Right? So this is a function that I would like to build. So I now have defined a function similar to the constant balance function. I have a different function f that takes in arguments and gives me a single bit as an output 0 when my input does not match what I'm looking for. And it gives me lights up with a 1 when my input string is the one that I'm looking for. Now if I were to do quantum mechanics, I would have to build this into a unitary operator and design my oracle around it. So exactly in the same fashion, I would like to build an oracle or a unitary that implements a unitary operator, and what this unitary operator does is the following. So there's a string of inputs, n qubit string, right, which is represented by this. Now this is not a single qubit, this is n qubits. It's a vector, it's a big multi-qubit vector, x. So that's why I put this in bold, right? And I have an ancillary qubit, say in the state q. And what this oracle does is very simple. It leaves the first register, which is a sequence of n qubits in the same state, and does an exclusive OR of the ancillary qubit with the function on. If this were my desired string that I'm looking for, this would become a 1. And if this is my undesired string, this would become a 0. So now I would like to build, so this is my oracle. This is my search oracle. And I would like to make this a part of an algorithm called the Grover algorithm. So now what I would like to do, suppose I keep my task simple. My x, this number is 2. So I'm looking for 2-bit strings. I'm searching amongst 2-bit strings. Right? So for 2-bit strings, the possibilities are 0, 0, 0, 1, 1, 0, 1, 1. Right? So this is my entire set of possible strings. There are 4 possibilities. My n equals 2, capital N equals 4. So I would need 2 qubits to encode these 4 states. Correct? And suppose that my desired string is this one. So what I'm looking for is 1, 1. This is my desired string. Now what I would like to do, so with this information I would like to build this unitary operator. That would be an oracle. So I've already built my quantum circuit that implements this oracle. Now can you, for example, how many qubits are now in this quantum computer? How many working qubits? How many working qubits do I have? 2. And 1 ancillary qubit. So I have 3 qubits. So I'm now attempting to build a quantum circuit. This is my x. right? So these two qubits represent my bold X. This represents my ancillary qubit. Now if I were to, for example, build what kind of, so if you just look at this problem from a classical perspective, what should I do? I would like to have some qubit that lights up, that gives me a signal that the two qubits that I'm looking for, each of them are equal to 1. What kind of logic gate would that be? AND gate, but an AND gate has 2 inputs and 1 output. So I need 2 inputs or 2 outputs, or 3 inputs and 3 outputs. So if I were to build a Toffoli gate, what the Toffoli gate does is that if it has both of these inputs are ket 1, then this input will be inverted, right? So it's a doubly controlled NOT gate. So if this is ket 1, this is ket 1, this third qubit will be inverted. So if I start this off in ket 0, this will turn to 1 if both of these inputs are 1. And by looking at this qubit, I can tell that I've found my search. My search has been successful, and the 2 qubits are in the state ket 1, right? So I would like to build a Toffoli gate. So my oracle, let's denote that oracle by O with sub f, because it's implementing this function f here, this one. This quantum oracle is taking 3 inputs, and it's really a Toffoli gate. So now I have one specific example of how to build an oracle. If I'm looking for 1, 1, this is what the oracle will look like. And if this bit is 1, it will flash that my 2 input states are ket 1 and I have found the solution. That's what an oracle means. It can determine, it can tell you, it can discern, it can discriminate when you have reached the solution from other possibilities. When you do not have 1, 1 here, this bit will remain 0. So the state of this qubit is going to tell you that you found a solution or not. So it can distinguish between, this circuit can distinguish between the solution and no solution. That's what an oracle means. Yes.
So this operation just or even both inputs are 1 or any other things?
Both of them have to be 1.
Just one possibility.
Right. No. So if you look at the unitary gate for the Toffoli, the matrix for the Toffoli gate, U Toffoli gate, it's an 8 by 8 matrix. 1, this is what the Toffoli gate looks like. So in this block here, you have a NOT gate. In other words, if you like to write the outer product formulation of this, this is if this is what the Toffoli gate looks like. If the first and the second qubit are in state 1 each one of them is in state 1, you apply a NOT gate to the third qubit. And if it's anything else, then you apply nothing to the third qubit. The third qubit just remains as it is. So this is just a shorthand for writing 0, 0, 0, 0 plus. So this really means is just a shorthand for this outer product computation. Okay? Yes. Either two inputs. So this Toffoli gate is a 3 input gate, 3 output. It has one. I mean, I do not understand your question. So there are 3 inputs, say 3 outputs. कौन सी? ये एक input आ रही है. This is just a control channel. This is the control line. This is not an input. नहीं. This is not an input, भाई. This is the control line. This is a control line. It's not an input. Look at the dimensionality of this. This is an 8 by 8 matrix. 3 inputs, 3 outputs. Anyway, I have to move on. So this is my implementation of the oracle. Now what do I do? Just as in the Deutsch algorithm, I would like to put a header mount here, a header mount here, a NOT gate followed by a header mount here, and then feed this into the oracle. This is a general scheme of many quantum algorithms. You input in the computational basis, ket 0, ket 0, ket 0. The ancillary qubit is inverted ket 1, and then you have a Hadamard gates on each of the 3 channels, and you create a big superposition. And then you feed this into the oracle. Right? So if you look at the state that is achieved over here, psi1. Let's see what state is fed into the oracle. I think this lecture will run a little bit over time. So state psi1 is simply a superposition of 0 plus 1 on the first qubit, right? Tensored with the superposition on the second qubit, tensored with the superposition on the third qubit, minus 1. Correct? And if I were to combine the first two qubits, I will get 0, 0, plus 0, 1, plus 1, 0, plus 1, 1. Now imagine this is an equal superposition. If you have 2 qubits, this is an equal superposition of all the 4 possible basis states, isn't it? An equal superposition of all 4 possible basis states. Just imagine the 2 qubits. And it's separable from the third qubit. Now just imagine how the third qubit is acting very cleverly here. It's in a sense becoming a symptom, and it's also becoming, it's helping you in shifting the phases here and there. So now what we would like to do is we would like to feed this into the oracle, OF. So when it is fed into the oracle, I generate a new state, psi2. Let's call this state over here psi2. Comes out here, right? This is my state psi2. Now I would like to implement my function, which is over here. The oracle implements the function in that fashion. It remains reversible, the same number of inputs, the same number of outputs. It does a logic gate, which in our case is the Toffoli gate. And you just apply the Toffoli gate over here. our output is going to look like the following. 1/2 So when the first two qubits are in the state ket 1, this changes to ket 1, this changes to ket 0. So this is inverted, so I put a minus sign over here. Got it? So I gave you 1 or 2 minutes to think about this, whether you understood this step or not. So why do I have a minus sign here? So remember that this is a different thing, right? This is a different piece of information. So if I expand this, if these are my two qubits, 0, 0, nothing happens to this, the third qubit. So this is 0, 0, 0, minus 1. If this is my first two qubits, nothing happens to this qubit. If this is my state, nothing happens to this qubit. But if my first two qubits, each one of them is in the state 1, this ket 0 becomes ket 1, this ket 1 becomes ket 0. So if ket 1 minus, so I just put in a minus sign over here. Now what I would like to do, I would like to do something more advanced here. I would like to implement a function here, an operator here. That operator is given by 2 times ket psi graph psi minus identity. So let's figure out later how do we implement this. And what is psi? My psi is an equal superposition of all the basis states. Now forget about the ancillary qubit. I forget about the ancillary qubit. I'm just looking at the first two qubits. My psi is defined as an equal superposition of all the 4 basis states, 0, 0, plus 0, 1, plus 1, 0, plus 1, 1, over, what should be the normalization factor here? Under 2? Just 2 here. So this is an equal superposition of all the 4 basis states. In shorthand, I could write this as 1 over under root n, where n is 4, capital N is 4, sum over ket I, where I goes from 1 to capital N, and ket 1 is defined as 0, 0, ket 2 is defined as 0, 1, ket 3 is defined as ket 1, 0, ket 4 is defined as ket 1, 1. So I'm just giving integer labels to these 4 basis states. Now let's see what is the action. So this operator now acts just on the first two qubits. I do not care about the ancillary qubit any longer. So it just acts on the first two qubits. Now what does this operator do? This looks like a strange kind of operator. Let's see what is the action of this operator. जी नहीं ये वाली I'm defining an operator. I'm defining this operator. This is some psi. What is this psi? That's how I define this psi. This is not psi 1, psi 2. It's just some psi. Good point. So what does 2 get psi drop psi minus identity do? So let's see what is the action of this operator on an arbitrary input state. Let's see what this function does. So if I take an arbitrary input state chi, how can I define an arbitrary input state chi? What's the general form of chi?
C1 cat 0 plus C2 cat. C1 cat 0 plus C2 cat 1.
So it's n cube. It's small n qubits now. So it will be a sum of all the cat i's with some amplitudes, right? AI. AI's are complex numbers. Correct? That's an arbitrary input state. Now let's see what is the impact of this operator on this state. Now this is a state, it's in ket form, it's a superposition of ket, so it is a state. Is this an operator? Yes, because it's an outer product, a ket, the bra, so it is an operator. The identity of course is an operator. So this operator is now acting on some arbitrary input state. So we're just going to find out what the action is of this operator on an arbitrary input state, and then we'll come back to the Grover algorithm. Alright, so if I just look at the operator, acting on chi, so this chi is given by 1 over under root n ket I, correct? Now the corresponding bra is given by 1 over under root n. I just use a different label now, j. Instead of I use j. I can't use I here, I have to use a different index here. This is j, goes from 1 to n, minus identity, of course is identity. And all of this is now acting on this arbitrary input state. Just a minute. Let's use k here. Yes. Sorry. Alright. So now let's expand this out. 2 times I, j, k. This becomes 1 over n. This gets an ak, I, j, k. Correct? Minus the same thing. Because identity acting on this leaves this unchanged. Now if you remember, these are basis states and they're orthogonal. So they are non-vanishing only when j equals k. So I can remove the j. Can I remove the j here? I can remove all the j's here, and I'll be left with 2 raised power 2 over n I k a k get I. So I can actually, so this is Dirac delta function delta jk. So what I could do is 2 over n k equals j. ठीक है. Just this piece. Just hold on. So this is just hold on. ये ठीक है ना? Just slightly lost in. Right. So if I just put this right, okay, 2 times got it? So this is, so I'm just connecting this ket with this summation. This is independent, this has no iota in it, so it just can be pulled out. Alright. So am I missing a factor of root n somewhere? So I can also write this as the following. Okay, got it. I'm good. So can you imagine what this thing is? This is a number, ak. It's a coefficient, it's a probability amplitude ak of a particular state. This state here, any arbitrary input state, and this is the sum of all those probability amplitudes. And then you divide by the number of states. So what does this look like? This looks like a mean amplitude, shabash. This is a mean amplitude. So this thing becomes 2 times the mean amplitude. Let's denote that mean amplitude by expectation value of A. A is just a complex coefficient over here, right? Now this is a number, a pure number. And of course I also have this sum of all the i's, of all the basis states, minus, now I can replace this index k with I, doesn't matter. So I can put this as I, AI, get AI. And this eventually becomes sum of over I of 2A minus AI So what is the impact of this operator, this strange looking operator, 2 times an outer product acting on an arbitrary input state? What does this operator do? Just look at the output there. What does it do? The input was this was the input here. Let me rewrite that input over here. Get guy is sum over I of AI complex amplitudes basis state get I. Now what the action of an operator to get psi, bra psi minus identity where psi is an equal superposition of all the states. What this does is that it just changes the complex coefficients. And how does it change the complex coefficients? Something really clever and strange. So if, suppose, let's look at this graphically. Suppose my input state were an equal superposition of all the states. So all of these were 1/2. So I'm looking at 2 qubits. Each one of this is 1/2. So I start off with so this is A1, A2, A3, A4. What now after this operation a new state is formed. That new state, of course it can be written down in the same basis. But now the complex coefficients have changed. Now how has each complex coefficient changed? You take twice the mean of this. So this is the mean here, the mean is here of all of these 4 values. Twice of this will be somewhere here. And from this twice you subtract this amount. So you will get, so when I do the subtraction, I get this. So I get back the same kind of distribution. It's of a different height. Each height is now equal to 2 times the mean minus AI. Fortuitously, it's the same in this particular example. But what if my input state is slightly different? What if my input state looked like this? If one of the amplitudes were negative, suppose my input state were this, say my chi were some, say, if this were my input state, still it's a legitimate state, normalized. But now the 4 amplitudes A1, A2, A3 and A4 look like this. One of them is negative. Suppose one of my input states is negative here. Now the average of these states will be somewhere here, right? Somewhere here, this will be the average of these 4 numbers. I take the double of this, I get somewhere here, 2 times this. Now I do a subtraction. So I get this height, I get this height, get this height, and I get, say, this height. So now the new state that has been created has the 4 amplitudes redistributed. 3 of them smaller and the 4th one really large. So if one of the amplitude is of a different sign, then this operator that we have in the Grover's algorithm is going to amplify that response. So now what we would like to do in the next class is to build on from here and see how the combination of this oracle and this operator, both of them together are called a Grover diffusion operator. How would they achieve this amplification? If this were to amplify so what we want to do is we want to amplify our desired search solution. If that desired search solution accrues a negative sign, which it really does over here. You see, all of these states which are not our solution, they appear with a positive sign, positive, positive, positive. But here, the solution that we're looking for has accrued or acquired a negative sign, minus 1. Right? So if I were to look at this state, psi 2 again, let me finish off this argument. In fact, we're almost done. After the oracle operator, my state psi 2 is really 1/2 0 0 plus 0 1 plus 1 0 minus, this is really important here, 1 over under 2 third qubit, the ancillary qubit. I don't care about the third qubit any longer. But now after the oracle operator, my desired solution has picked up a negative sign. And if this were to be followed by that amplification operator, the end result is expected to be one in which this probability amplitude corresponding to this state is enhanced and the amplitude corresponding to these 3 states is diminished. So my output state will be brimming with the desired solution. So before we meet on Wednesday, what I would like you to do is apply the Grover operator, the amplification operator, sorry, onto this input state and tell me what the state would be at this location, psi 3. Now that we know what the action of the amplification operator looks like. So I would like you to precisely determine the probability amplitudes. In the next lecture, we would like to start off with that. So I will look at your notebooks and see if you are able to find out the action of that amplification operator. So the solution is amplified in its response and then we can detect it. So in the next lecture, we would like to look at this from a geometrical perspective. I would like you to write the unitary operators for this. I would like you to write down what the quantum circuit for that amplification operator will look like. We already have a quantum circuit for the oracle. So what kind of quantum circuit will implement this amplification operator? And how many queries are needed to find out the exact solution? If our search string space is bigger, if instead of 2 qubits you have 3, 4, 5 qubits, how long would it take? What kind of speed up does this promise over other classical counterparts? Classically, if you have small n qubits and capital N strings, how many search queries would you need in the worst case scenario? N squared. So there are n, capital N strings You want to search for one particular string. How many, in the worst case, how many queries would you need? How many times would you need to look up your directory? Order of? No, n. N minus 1 really. So, in the worst case scenario, you would have to do capital N searches. Because the string that you're looking for might be at the very last location that you look. So, really n minus 1. Capital N minus 1, or of the order of n. Here we get a quadratic improvement over the classical counterpart in terms of query complexity. The time complexity may actually go up as well because you have to implement all of this in quantum logic gates and it might not be easy to do on a quantum computer. So we're going to build up on this. So please come on Wednesday equipped with a calculation of what's going to happen when the amplification operator acts on the state cycle. And then we look at this from a geometric perspective and find out the complexity. How many iterations would be needed to perfectly zoom in onto the solution? All right, thank you very much.